Hello students, welcome to EPG Pathshala. I am Dr. Aditya Saxena from the Department of Physics, Central University of Haryana. Today, we are going to discuss about the module Functional Vector Space and Operators under the paper Quantum Mechanics 1. So students, let us see what we are going to learn in this module. Firstly, we learn how a linear vector space is finite dimensions can be generalized to functional vector space. So, we'll discuss the conditions under which this generalization can be done. Secondly, we'll know the properties of infinite dimensional vector space. Thirdly, we'll learn the concept of Hilbert space and also know the essential criteria that a Hilbert space is supposed to satisfy. Further, we'll also know that in case of a Hilbert space, if the linear vector space satisfies the desired criteria, the Hilbert space can be both finite dimensional as well as infinite dimensional. Then we'll get to know the properties of linear operators, which means we'll start understanding what is meant by the term operators and how they work. After that, we'll learn the matrix representation of a vector and a linear operator. Now, students, having learned the basic properties of linear vector spaces in finite dimensions in the preceding module, we shall in this module generalize to functional vector spaces and to infinite dimensional vector spaces. This would eventually lead us to introduce the concept of Hilbert space, which has a pivotal role in the formulation of quantum mechanics. The next section is devoted to studying the properties of linear operators which have the effect of transforming a vector in the Hilbert space and relating it to a new vector. So in this manner, we will try and understand how a linear vector space behaves as a Hilbert space, what is the utility and the use of having a linear vector space as a Hilbert space, and finally we'll then start defining our formalism in terms of the Hilbert space and define the various operators and their operations in the Hilbert space. Functional vector space. Now we will discuss the concept of functional vector space and the various terms associated with it. First of all, let us come on to the concept of unit vectors or bases that is discussed so far, and this can be generalized to functional vector spaces. Let a set of n linearly independent functions phi I x, that is phi I as a function of x, where I is going from 0, 1, 2, so on till n minus 1, and where x is a variable, span the n-dimensional vector space. Then all polynomial functions like phi x, psi x, xi x of degree m less than within brackets n minus 1 can be expressed as a linear combination of phi I as a function of x. That is, for example, we can have psi x is equal to summation going from I equal to 0 to I equal to capital N minus 1, Ci phi I x, where Ci is some coefficient and phi I x are the n linearly independent functions. And the functions phi ix, which is the basis, constitute a set of complete set describing all polynomials of degree m less than within brackets capital N minus 1. The functions of the linear function space satisfy all the properties of vector addition, that is, they are commutative, which means that if we have two functions phi x and psi x, both functions of x, then we can write phi as a function of x plus psi as a function of x is equal to psi as a function of x plus phi as a function of x. They also satisfy the associative property, which means that if we have three functions phi x, psi x and xi x, then phi x plus bracket open psi x plus xi x bracket closed is equal to bracket open phi x plus psi x bracket closed plus xi x. Then we also have the null identity. That means that if we have a function phi x and a null vector 0, then we have 0 plus phi x is equal to phi x plus 0 is equal to phi x. We also have that these functions satisfy the multiplication of vector by a scalar, etc. So, which means that they are distributive. Let us consider two functions phi x and psi x, and let us define a scalar alpha. Then alpha into within brackets phi x plus psi x is equal to alpha into phi x plus alpha into psi x. The scalar multiplication is also associative. So, if we have two scalars alpha and beta and a function phi x, then we can define the associative property as alpha into within brackets beta phi x is equal to within brackets alpha beta into phi x. And then we have the identity property, which means that if we have an identity vector I and a function phi x, then I into phi x is equal to phi x. Properties of linear function space. The inner product of two functions phi x and psi x is defined by the inner product or scalar product of functions phi x and psi x is equal to integral of phi star x into psi x dx. The inner product has similar properties like the scalar product or the inner product of phi and psi is equal to the scalar or the inner product of psi and phi star, which means that it is equal to the complex conjugate of the reverse of the original scalar product. The inner product also has the following properties. That means, one, that it is commutative. So if we have two functions phi and psi, then the scalar product of phi and psi is equal to the complex conjugate of the scalar product of psi and phi. It is associative, which means that if we have two functions phi and psi and a scalar lambda, then the scalar product or the inner product of phi and lambda into psi is equal to lambda into the inner product of phi and psi. The inner product is also distributive. So if we have three functions phi, psi and xi, then the inner product of phi and psi plus xi is equal to the inner product of phi and psi plus the inner product of phi and xi. And finally, the inner product of phi with itself is always greater than or equal to 0. Then we come on to infinite dimensional vector space. So let us define what is the Hilbert space. The theory of a linear vector space of finite n dimensions discussed earlier can be generalized to infinite dimensions by taking the limit n tends to infinity. Vector spaces which have finite dimensions are of basic interest in quantum mechanics. Vector spaces which have infinite dimensions are of basic interest in quantum mechanics. Consider the space of infinite sequence of numbers x1, x2 and so on, xk and so on up to infinity, such that summation k equal to 1 going to infinity, the square of the modulus of xk is finite. Concept of Hilbert space. Now we will discuss the concept of Hilbert space and the various properties that are associated with it. So we start with discussing the operations of addition, scalar multiplication and scalar product in the Hilbert space. First of all, we start with the operation of addition. If we have two infinite sequence of numbers x and y which are defined such that x plus y is equal to x1 plus y1, comma, x2 plus y2, comma, so on, xk plus yk and so on till infinity. Then we come on to the scalar multiplication. So let us define a scalar x. Let us define a scalar a and a sequence of numbers, that is an infinite sequence x, such that ax is equal to, we have the sequence a x1, comma, a x2, comma, so on, a xk, comma, so on till infinity. Then let us define the scalar product of infinite sequence of two numbers or two vectors. So if we have an infinite sequence of two numbers x and y, then the scalar or the inner product of x and y is defined as summation k going from 1 to infinity xk star yk, where xk star is the complex conjugate of xk and where x is the infinite sequence defined by x1, x2, so on till xk, so on till infinity, and y is defined as y1, y2, so on, yk and so on till infinity. This space, that is the Hilbert space, which has denumerably infinite number of dimensions, is defined as the Hilbert space, or the space which has denumerably infinite number of dimensions is called a Hilbert space. A Hilbert space is a unitary space that is complete. That means it has the property of completeness, or it satisfies the property of completeness and is unitary. Further, it has an orthonormal basis consisting of the vectors u1, that is vector u1 is equal to 1, 0, 0 and so on. Vector u2 is equal to 0, 1, 0, 0 and so on, and etc. That means we can define like this vectors u3, u4 and so on. Orthonormality and completeness. Now let us look at the conditions of orthonormality and completeness in the Hilbert space. So, such that only non-zero number in uk is xk, which is equal to 1. This space is called L square, and any arbitrary vector x in L square can be written as x is equal to summation k going from 1 to infinity xk into uk, and the sequence of vectors xn can be defined as xn is equal to summation k going from 1 to infinity xk uk is a Cauchy sequence whose limit vector is x. So what this means is that if we have a sequence of vectors xn which can be defined as defined above, such that we can also define another arbitrary vector x in the same space, that is the L square space, as defined above, then the arbitrary vector x is said to be the Cauchy sequence limit vector of the Cauchy sequence, that is the vectors xn. So, to sum up, what we can say is a linear space, whether it is finite or infinite, and that 1 has inner product defined and 2 is complete, is called a Hilbert space. So in this manner, we can define what a Hilbert space is. Basically, a Hilbert space is a linear vector space which may be finite or infinite, but which has 1, its inner product defined, and 2, which is complete or follows the property of completeness. Then we come on to orthonormality. So, orthonormality and the completeness of a set of vectors in the space L square. For defining this, let us suppose that phi within square brackets infinity is an orthonormal basis for an infinite dimensional Hilbert space. That is, the scalar or the inner product of phi k and phi l is equal to delta kl, where delta kl is equal to 0 for k not equal to l and is equal to 1 for k equal to l. Then any vector psi in the space can be expressed as a linear combination of the phi k's as defined above. So we can write this mathematically as psi is equal to summation k going from 1 to infinity ak phi k, where ak are the coefficients in the expansion. Square integrable function space. The coefficients ak in the expansion for psi equal to summation k going from 1 to infinity ak phi k are unique and are given by al is equal to summation k going from 1 to infinity ak into the inner product or the scalar product of phi l and phi k, and is equal to the scalar or the inner product of phi l and psi. Thus, we have that psi is equal to k summation k going from 1 to infinity phi k into the scalar or the inner product of phi k and psi. If the vectors phi k are square integrable functions, say of a variable x, then we have the condition for the orthonormality given by the scalar or the inner product of phi k and phi l is equal to integral phi k star x phi l x dx is equal to delta k l, where phi k star x is the complex conjugate of the function phi kx, and delta kl is equal to 1 for k equal to L and is equal to 0 for k not equal to L. This gives us the relation psi x is equal to summation k integral phi kx phi star k x prime psi x prime dx prime. But since psi x is also defined as psi x is equal to integral delta x minus x prime psi x prime dx prime. Therefore, on comparing the two equations, we get summation k going from 1 to infinity phi kx phi star kx is equal to delta x minus x prime, and this condition is also called the completeness condition. Here delta x minus x prime is equal to 1 for x equal to x prime and is equal to 0 otherwise. The equations defined above, which express the orthonormality and the completeness conditions, are of basic importance, especially in Schrödinger formalism, with the wave function space being actually square integrable, that is L square within brackets minus infinity comma infinity. Properties of linear operators. Now let us understand what are the properties of linear operators and how, when these linear operators operate upon any vector, how does it transform? So, an operator acting on a linear vector space gives us a relationship between the two vectors, say psi A and psi B. A few typical examples of linear operators in which we shall be concerned here are 1. Differential operator, 2. Translation operator, or 3. A rotation operator. For example, a translation operator or a rotation operator acts on the vector psi A, resulting in the vector psi B, which is mathematically expressed as psi B is equal to operator A acting on the vector psi A, where the effect of the operation of such an operator is to cause either rotation or also cause some kind of a transformation. Then we define an operator A such that it is said to be linear if operator A acting on the vectors psi1 and psi2 in such a manner that, supposing if we have two scalars alpha and beta, then operator A acting on scalar alpha into psi1 vector plus scalar beta into psi2 vector, and this is equal to alpha times operator A acting on psi1 plus beta times operator A acting on psi2 for every pair of vectors psi1 and psi2, and for every pair of scalars alpha and beta, whether they are real or complex. Properties of linear operators. An antilinear operator, on the other hand, is defined by operator A acting on, within brackets, alpha psi 1 plus beta psi 2 is equal to alpha star within brackets operator A acting on psi 1 plus beta star within brackets operator A acting on psi 2. Here psi 1 and psi 2 are the pair of vectors, while alpha and beta are the pair of scalars which may be real or complex. Further, alpha star is the complex conjugate of the scalar alpha and beta star is the complex conjugate of the scalar beta, and A is the operator that is acting on the vectors psi 1 and psi 2. The null operator O and the identity operator I are respectively defined by operator O acting on psi is equal to 0 and operator I acting on psi is equal to psi. Now, the two operators, operator A and operator B, are said to be equal, that is, operator A is equal to operator B, in the sense that operator A acting on psi is equal to operator B acting on psi, where psi is any linear vector in the linear vector space Vn. Also, operator A is greater than operator B if the scalar or the inner product of the vector psi and operator A acting on psi is greater than the scalar or the inner product of the vector psi and operator B acting on psi for all psi in the vector space. Now we come on to the addition and the product of two operators, and we define the sum of two operators, that is operator A and operator B, such that if we have another operator C, then C is equal to operator A plus operator B is defined if for every vector psi we have operator C acting on psi is equal to operator A acting on psi plus operator B acting on psi. Similarly, product of two vectors, that is two operators, operator A and operator B, can be defined as operator C is equal to that is, we can define another operator C such that operator C is equal to operator A into operator B if for every vector psi we have the operator C acting on psi equal to operator A acting on, within brackets, operator B acting on psi. Commutative property of operators. Now let us look at the commutative property of operators, and it is seen that in general the operators do not commute. What that means is that if we have two operators A and B, then operator A into operator B is not equal to operator B into operator A. Note that the domain of the product of the operators A and B is a subspace of the domain of operator B, whereas the domain of the product of operator B and operator A is a subspace of the domain of the operator A. Thus, we have that for every vector psi in the domain of the operator B, the operator B acting on psi may not be in the domain of the operator A, and thus may not be in the domain of the product of the operators A and B. However, when the two operators, that is operator A and operator B, commute, which means that the product of operator A and operator B is equal to the product of operator B and operator A, the domains of operator A and operator B and the product of operators A and B coincide. That means that they have the same domain. A typical example is when you consider the space of a square integrable function of x. Suppose we define an operator A as operator A is defined as x, and we take another operator B which is defined as operator B is defined as the derivative with respect to x, that is d by dx. Then we see that the product of the operators A and B minus the product of the operators B and A acting on some function fx, which is a function of x, is equal to minus identity operator acting on the function fx. From this expression, one can see that, or one can show that the operator x into d by dx minus the operators d by dx into x is equal to minus I operator, or in other words, the way we have defined the operator A and B above, we can see that the commutation, we can see that x into d by dx minus d by dx into x gives us the identity operator in the negative. Inverse of an operator, singular and non-singular. Now we define the inverse of an operator. So let us consider two operators, operator A and operator B, such that they satisfy the relation operator A into operator B is equal to operator B into operator A is equal to the identity operator I. Then the two operators are said to be reciprocal to each other. The operator B is then defined as operator B is equal to operator A inverse and is called the inverse of operator A. An operator for which an inverse exists is called non-singular, and an operator for which there is no inverse which exists, such an operator is called singular. A necessary and sufficient condition for an operator to be non-singular is that corresponding to each vector phi, there should be a unique vector psi such that phi is equal to operator A acting on the vector psi. The inverse of a product of operators is the product of the inverse in reverse order. Mathematically, this can be shown or written as the product of operator A, B and C within brackets whole inverse is equal to the inverse of operator C into the inverse of operator B into the inverse of operator A, or is equal to the product of the inverse of operator C, operator B and operator A. Now let us consider an operator A which is operating on a vector x and transforms it to a vector y such that vector y is equal to operator A acting on the vector x, where the vectors x and y are given by x vector is equal to summation over I xi ui, and the vector y is given as vector y is equal to summation over I yi ui. So we have the vector y is equal to operator A acting on x, which gives operator A acting on summation over I xi ui is equal to summation over I xi operator A acting on ui is equal to summation over I comma j xi cji uj. Matrix representation of operators. Continuing from the previous equation, we see that we have defined the operator A acting on ui is equal to summation over j cji uj. Now, since the vector y is equal to summation over j yj uj, therefore, on comparison with the above equation, we find that yj is equal to summation over I cji xi. We can rewrite it as yj is equal to cji xi. Here we have used the convention that when an index appears twice, it is to be summed up. The components of the vector are expressed in a column matrix. So the vector x can be written as a column matrix x1, x2, so on, xn. And the numbers such as c equal to cji is represented by an n cross n matrix, and this is given as within the matrix you have the elements c11, c12, c13 and so on, c1n, then c21, c22, c23 and so on till c2n, then c31, c32, c33 and so on till c3n, and so on till we reach the nth row cn1, cn2, cn3 and so on till cnn. Matrix equation. We can now write the equation A defined earlier, which is that yi is equal to summation over I cji xi as the matrix equation y is equal to cx, which is a representation of the operator equation vector y is equal to operator A acting on vector x, with the column matrix representing the vector x, the n cross n square matrix representing the operator A, and the column matrix representing the vector y. So the vector y column matrix can be represented as y is equal to column matrix y1, y2, y3 and so on till yn, and the corresponding orthonormal set ui is represented as the column matrix u1 is equal to 1, 0, 0, 0 and so on till the nth row 0. u2 is represented as 0, 1, 0, 0 so on till the nth row 0. u3 is represented as the column matrix 0, 0, 1, 0, 0 and so on till the nth row 0, and so on till the un column matrix is represented as 0, 0, 0 and so on till the nth row whose element is 1. So students, now let us summarize what all we have learned in this module. So when we went through this module, we got to learn how a linear vector space in finite dimensions can be generalized to functional vector space. And we also learned about the various rules and the various terms that are there because of which this generalization can be done. Then we moved on to know the properties of infinite dimensional vector spaces, where we discussed the different properties of infinite dimensional vector space in terms of the addition, the multiplication, and the scalar product. After that, we also discussed and learned the concept of Hilbert space, and we got to know the essential criteria that a Hilbert space is supposed to satisfy. In this manner, we were able to define what the Hilbert space is and under what conditions a linear vector space acts as a Hilbert space. After that, we proceeded to know the properties of linear operators, where we studied how these operators act upon the different vectors and what is the consequence. That means what is the kind of transformation that these operators bring into the vectors. And we saw that basically these operators help in doing some kind of a mapping between one basis vector set and another basis vector set of the same space. After that, we also learnt the matrix representation of a vector and a linear operator. Thank you.